Hello, everybody. In the first part of my talk, I explained our simulations, molecular dynamics simulations of GLIC. And as we all noticed, there were some problems with it. The most important problem was timescale problem. We know that conformational transitions happen about from 100 microseconds to milliseconds for GLIC or for pentameric ligand gated ion channels in general. But the timescale that we can reach is a few microseconds. So the timescale is not sufficient to see conformational transitions, to see impact of ligands or impact of agonist binding, etc. But still, we can get some information. It was not sufficient, so I decided to do some coarse-grained studies, and in these coarse-grained studies we modeled GLIC as a mechano-elastic object. So this is the second part of my talk. So what do we mean by mechano-elastic object? So we assume the protein is an elastic object, basically a mass spring system, and we connect all C alpha atoms within a certain cutoff radius with springs. Our aim is to study allostatic interactions with this method. You see an example here, a very simple example basically. You put just springs between C alpha atoms. So we will do the same thing for the entire GLIC. But the methodology, after building your network, elastic network basically, we will apply force locally and then measure the displacement over the entire structures. So for example, we will apply force to the 5th atom and the 7th atom, and then we will try to response of 5th and 7th, but additionally all other atoms. And in this way, we will try to mimic or model agonist binding and how a local change can propagate to the entire protein. So as I said, we will try to measure the displacement for all atoms for the entire structure. That's exactly what we did. Now let me explain this plot in this slide. So I am applying force to loop C that I have shown in the previous part of my talk, in the introduction part. If you want, you can go there. And these are the top plot is where the force is applied, and the amount of force is shown here. Amount of force is not identical between the different chains, subunits, but still it is more or less very similar. The force is proportional to the delta R between the open conformation, closed conformation, and the open conformation. So that's the reason it's not same for all atoms. And when you apply force to loop C, you can, of course, loop C part is the biggest responding part, as you can see here, here, and here, and here also. But in addition to loop C, we can see a response in other parts of the protein. Like in TMD also, you can see a peak here, for example, and again peak here, and again peak here in TMD peak. And again, finally, a peak here. Now we projected the force, delta R, the response, not force. We projected response onto protein structure. So, as you can see, of course, when you apply a force, the biggest response is on the local part. But you can see on TMD also, you can see that there is a response. Here, the response is in a color scale from RGB, and red is low response, green is medium response, and blue is high response. So we can see that, for example, if we apply a force to loop C, which is an agonist binding site, the protein responds it in TMD also, not just locally. Now let's do this in the reverse way. What if we apply force to M2, which is the helix lining the pore, and we apply the force to just M2 we apply force to make it open like, starting from the closed structure. As you can see, if you apply force to M2, you can see here the blue part. You can see a response even on the top part of the protein, not just in the TMD. Interestingly, even though the medium, I mean the ECD part between TMD and the top part showing low response, the top part is showing high response, and actually the loop C part. So if we model the system as a mechano-elastic object, we can see that a local force can propagate to the quite far points, and the distance I am talking here about, for example, here it's about at least 40 angstroms. So we wanted to test the robustness of this method. We changed the direction of the force, and when we changed the number of normal modes, but still in general you can see long distance impact of local force. So it's the method, or this methodology is robust in general. Now another question that we wondered, what if the conformational transition is not just happening across the entire subunits at the same time, and what if it happens sequentially? Actually, in molecular dynamics simulations, we observed that, for example, locally closed states change between interchange actually between closed and locally closed states at ECD level sometimes, at TMD level sometimes, but it was not happening across the entire protein. So we wanted to observe that. We applied force to just one subunit, subunit A, to make it from closed state to make it open-like state. And when you apply force, actually you can see a response. You can see a response, but a decreasing response across the entire protein. You see the peak here, and the same peak is reducing and reducing again. So the force on one subunit affects the neighboring subunit in clockwise direction. And now I am applying a force just to the ECD of chain A, but sorry, I am observing again a decreasing force in ECDs of the neighboring chain. The biggest chain that's affected, as you can see, is the neighbor one. Here, for example, chain B, and the force reduces, but it goes to chain C, etc. And again, the same idea is applied here. You can see that if you apply to a force to chain M2 of chain A, it's propagated to the neighbor chain, and it's propagated to the ECD of the chain, etc. Now I want to go back to my LMI maps to finish this section with a model of how force and fluctuations propagate through the protein. I have shown you LMI maps for the entire structure, and here you can see a zoom in for chain E, and here you can see a zoom in for a particular part of chains AB, interchain correlations, and here you can see chain AC correlations, or linear mutual information, for a non-neighbor chain. Chain AB are neighbors in clockwise direction. That's an important point to note. Just in general, I want you to take a look to the patterns. Here, for example, in the ECD and the TMD, we have high correlations. And again, look at the chain AB block. TMD, and on the ECD, it seems like in general here, it seems like two neighbor chains behave like an individual subunit. Chains AB, this is part of chain AB again. But if they are not neighbors, like chains AC, yes, still we can see some low correlations, but the correlations are quite low. So here I am showing some details. We projected the correlations onto protein structure, and as you can see, on the ECD level is this part projected onto protein structure, and you can see that two neighbor chains, let's say, interact with this is intrachain. Intrachain correlation, we can see a high correlations inside the chain on ECD and on TMD level. Let's go to the interchain. That's the important part for us. Here you can see chains AB from the top part. Chains AB has two faces basically, and these two faces make it behave like a single subunit. On TMD level also we can see the same thing. Again, it behaves on TMD level also, it behaves like a single subunit. There are some important loops between ECD and TMD. And these loops, for example, one of them is loop F. Here you can see a high intrachain correlation for loop F, and high intrachain correlation for pro-cis loop. And again, beta 1, beta 2 loop also show high correlations. So these are important loops that transmit fluctuations and probably transmit force also. Let's take a look now the same thing for the interchain interactions. You can see that, okay, loop F is still effective. The same residues are interacting for the neighbors. Loop F is interacting with M2, M3 loop of the neighbor chain. That's the important part. You can see that pro-cis loop of one chain is interacting with M2, M3 loop of the neighbor. And again here, beta 1, beta 2 of chain A or subunit A is interacting with the M2, M3 loop of chain B. But there is an important part. Just look at here. You can see that the interactions are not symmetric. Normally for an interchain, let's go back. For intrachain, it is symmetric. You can see the same thing here and here also. But for interchain interactions, it is not symmetric. There is a clockwise direction. I mean, there is a directionality for the propagation of fluctuations or correlations, linear mutual information. So, and again, these results are in agreement with our force analysis also. So based on force propagation and fluctuation propagation, we propose a plausible model. This model is called ZI model, and I denotes interchain interactions and Z denotes interchain interactions. Let's take a look. As I said, between ECD and TMD there are interactions. At the interface also there are intrachain interactions. Top part of Z means that there are two ECDs, two neighbor ECDs are interacting with each other. Bottom part of Z also says that two TMDs, two neighbor TMDs are interacting. And the diagonal element of Z tells us their loops are also interacting, and these loops, for example, propagate force and fluctuations, can propagate force and fluctuations between ECD of chain A to TMD of chain B. Okay, I would like to finish my second part with the conclusions. So according to this mechano-elastic model, we can explain how local changes propagate to the entire structure. For example, we saw that loop C can affect both TMD and ECD, and similarly we saw that changes in M2 helix can affect both TMD and ECD also. Here, and these simulations support the idea of a sequential change. And if that is the case, ZI model is a plausible model. How a sequential conformational change can happen? So basically, it says that there is a direction, clockwise direction of propagation of fluctuations and force, and fluctuations and force propagate through neighbor interactions. I would like to finish my talk here, and if you have some questions, please write as a comment or just send me an email. Have a great day.